The three possible outcome. First one was ordinary causal form. Everything nice and easy. You have here then sort of the working procedure, how to find the state equation. So this is a little self-study if you are still not comfortable how the sequence is, how you should annotate these graphs after finding all the causal strokes. I mean, the sequence here can be a little bit confusing, so definitely some training is very important here. I mean, this is where you can start after here finding everything is causal. You get the stroke here and here, yes, and then you can write this up instantly for the I and C elements that has the correct integral form. Also, you know the effort source here. So this is where you begin. But where to continue? You can't really, yeah, that's also a common mistake. A lot of people, they will say, here I have an effort called P dot. And here I have a flow called Q dot. Well, shouldn't I then, can't I then use Q dot as flows for the other bonds as well? No. These should appear only once in your bond graph, so don't spread them around. That would be dangerous, like some bad example here, but let's do the other way. If you have a 0 and an I element, and this was on the integral form, okay, then instantly you will here write P dot and P over I. And here you have some other bonds, some go in, some go out, for this is zero junction. Now one might be tempted to say P dot, okay, it's a common effort. Don't I have P dot here as well, and here as efforts all around this zero junction? No. P dot should appear only once in your bond graph. So to continue here, where should you go? Well, you look at the one junction here and the zero junction here and ask, who is dictating the common flow? Who is dictating the common effort? For this one junction, that is where you are missing a stroke. Aha, the common flow, it's P over I. Then you can write P over I as a flow here. Well, for the source you have an X already, so he's not interesting. But here, yes, that's the flow, P over I. So this one you can now write directly. For the zero junction, that's common effort. Who dictates the effort? That's where you have a stroke. Aha, so the effort is Q over C. Then instantly Q over C here and here, as you can see. So this will be sort of the way you should work. And here, finally, you are just missing one flow from the resistance. Okay, you have the effort. Easily to calculate the flow, just divide by R. So that will be a working procedure. Of course, training. So you'll have one mechanical bond graph now in exercise 3. You will have 16 problems in exercise 4. Exercise 4, very important exercise. That's where you learn bond graph. Cute, small little problems, but you have to do everything, finding the differential equations in the end. And here, where are the equations? Where are the equations? Well, use the summation rule around the one junction and the zero junction. The sum of all efforts has to be 0. Then you will have one equation involving the P dot. For this is 0, you will have the sum of all the flows. Then you will have one equation involving Q dot. So that's how you find your state equations in the end. Yeah. Never mind that. I won't bother you with these simple causal problems. I will jump to an over-causal example. here I have, say, a solid plank or something, and he can tilt around one common point there, so he's not in balance, but he can flip around this point, sort of actually rotate around this point. On this end I put mass number 1, and he is attacked by a force as a function of time. The length, I call this one A and this one B. And then on the other side I have another mass, M number 2. And then here I have a spring attached to the ground. So this is my problem. Find the state equation and well, bond graph first, state equations afterwards. So how should we do this? We assume very small angles. So he doesn't really rotate. We only look at up and down motion here, small angles. If we draw it like this, here, point, and all the way up here. So if I overdo it a little bit, like this, A and B. So if this distance now is x, what do I get on the other side? I get a y. But I would assume that x and y, they only move up and down. The mass 1 and 2 only moves up and down. If the angle is not too big, that should be a good simplification. So what's this coupling? You have up and down motion on the left side, up and down motion on the right side. So clearly they are coupled. What's the coupling? Is it a transformer or a gyrator? Well, if you move a distance x down here, then you know the distance on the other side if the geometry A and B are given. I mean, the angle is the same, so you will have, what will it be? X divided by A equals y divided by B, right? And then if you take the time derivative of this equation, you will have the velocity on the left side is coupled with the velocity on the right side. Ah, it must be a transformer. Yes, of course it is a transformer. And what was the transformer definition? Well, if you had one flow here, what was the flow on the other side? Well, that was t multiplied with the first one. So what's my value of t in this problem? Well, from this equation here, you find y dot equal to. So this means my t has to be b divided by a. That is my transformer. Okay, let us draw the bond graph for this problem. Here I have something moving with its own velocity, one junction, and he is attacked by an effort, and I have a mass attached to this one junction here. Now this motion is coupled to the motion over here through a transformer. So I will have something like this. And then on the other side, I have one junction. He has his own velocity. And here I have a mass. I will have I2. And then I have a spring. How did we do it with spring? Well, you use a 0 and then a C. But here I have ground when I continue, so it's going to simplify to just a spring like that. So now we have gained enough experience, I would say, so that we can simplify skipping the ground directly. So here I have my raw bond graph. And can I simplify it? No. I can't, can I? Nothing can be simplified. If I had only one I or one C on the right side, then I could use this equivalence, transformer and one element. Yes, then I could do that trick. But here I have two, so no, you can't really do any simplifications here. Okay, let's do the working procedure for the causal strokes. Start with sources. Effort source, given. Then that stroke didn't dictate anything. Okay, then I choose. And I have a mass here. I choose integral form for him. Okay, then this one junction now dictates it has to be a stroke here, because he only wants one stroke away from him, which I now found for I1. The transformer, well, a stroke here instantly dictates a stroke here for the transformer. He doesn't change the causal strokes. Then for this one junction on the other side, he has already been decided what bond should be away from him. Okay, then it has to be like this. Well, what do you know? I have this C element that is with the integral form, but this mass, no, he is on the differential form. So now how to find the equations? Well, from the source I have the force. That one is known. I1 is on the correct form, so here I have a P dot with a circle. I should call him P1 dot. On the other side, P1 over I1. This C element is on the correct form. The flow is a Q dot with a circle, and on the other side, effort Q divided by C. This you can write instantly when you have elements, C elements on the integral form. For I number 2, just leave him for now. He doesn't give any new differential equation. Actually, that should be possible to see directly from the figure, from the problem. I mean, it goes without saying, doesn't it? If you think a little about it, you have one motion for mass number 1. If you know this motion, well, then you know the motion for mass number 2. Of course, you shouldn't have two different differential equations to describe the same motion. I mean, they are directly coupled. And if you had chosen differently here on this bond graph, you would have gotten the same, but then maybe this one would be on integral causal form. Then this one would definitely be on differential form. We can try that afterwards. Okay, let's continue. And how do we continue? Let's see now. We can try with this one junction here. That's a common flow. Who decides the flow? That's where we're missing a stroke. Then I need a flow here, but I don't have a flow there. A flow here must come from here. Well, I don't have the flow here either, do I? Okay, then I better start with this one junction. Who decides the flow? That's where you're missing a stroke. It's this P1 over I1. Okay, then I know the flow here. P1 over I1. And I know the flow for the source as well, but that's not interesting. Then we go through a transformer on the other side. What do you get? Well, you have just multiplied with T. So here, T multiplied with P1 over I1. There we have now the common flow around this one junction. And also, physically, it makes sense, doesn't it? If you know the motion here, he dictates the motion on the other side. Of course he does. Okay, now we have the common flow for this one junction. Well, I have something here for the flow already, a Q dot. That would be my first differential equation. So we write that one down instantly. Q dot equals T multiplied with P1 over I1. That's one equation. Let's continue. Common flow here. Then I have something flow here. It's called TP1 divided by I1. And he is now sort of a flow hitting my inertance number 2, which was on this differential form. What should be on the other side here? Aha, it was time derivative of the flow and then multiplied with the inertance. So it will be TP1 over I1 multiplied with I number 2. And then the time derivative of everything there. That is my effort here. When the bond graphs get a little too small, you have a lot of algebra inside the bond graph. You can use then symbol A. And then you write A equal and so on. What will actually this A be? Most of these are constants except P1. P1, time derivative, that's P1 dot. But the rest, they are just constants. So it will be T multiplied with I2 divided by I1. So that is my A. Okay. We are still missing something, aren't we? I need some efforts here. Who should dictate the effort? Well, say here I have an effort. I can find him by taking the summation rule around this junction, but I would rather go the other way around. Remember, efforts, they go towards this causal stroke. So the effort here would go this way through the transformer, finding this one. So I will calculate him first, call him B. What is B? Then you have the summation rule around the one junction. The effort here, he goes in, my positive direction, equals what goes out. So I have one effort down here. It's Q over C. And then I have one other effort here called A. So there I have my effort now called B. What do I get on the other side of the transformer? You just multiply it with T. And then finally, the summation rule around this junction. Then I have what comes in. It's a force, F. Effort in equals effort out, equals my P dot plus TB. There I have my two differential equations. Now let's see what happens. Yeah, we'll leave this one. We don't need anymore. So of course you write it on the form P dot equal to. You will have the force minus T multiplied with B. B, that was Q over C, plus A, which I have up here, P1 dot, transformer, I2 over I1. Actually, this one should be P1 dot. And there you see the effect of this differential causal form. Well, for the first equation, that was okay. Then second one, the P1 dot differential equation, the P1 dot appears two places. So we are going to need a little bit algebra for the last one there. P1 dot equal to, so this term has to be thrown on the other side. So what are we left with? P1 dot equals force minus transformer Q over C divided by 1 plus, and then we will have transformer squared, and then the ratio I2 divided by I1. Yeah, it says the same here, so that must be correct then. Any questions to that one? It's a little bit mechanics here, but if you multiply with I1, let's see, on both sides here, you will have, what do we mean? No, you have to divide, you have an I1 inside here. Then you will have I1 plus T square I2. That's sort of an equivalent rotational mass. So that would be possible to use rotation. Then you would just have one single mass rotating. But that's a different story. I want to check if this can be correct. How can we check it? Well, I have one equation here and another one there. Use this one now and create a second order differential equation. So say a check Q double dot equal. It will now read something like this: T divided by I1 multiplied with P1 dot, and then you insert this one equals, and then you get some nasty expression. You will have something like this: Ft minus T square Q over C I1 plus T square I2. Okay. So we got the equations, we got the bond graph over causal, and I started to choose for I1. Now let's do the other way. We had an effort source, one junction, mass number 1. We had a transformer, another one junction, mass number 2. And we had a spring. That was our bond graph. Now start applying causal strokes. Start with the sources. Then nothing is dictated, hence we choose one of the I and the C element. Let's start with the C element. I choose for him first. Then I choose the integral form, like that. But that doesn't dictate anything. For this one junction, he needs all but one towards him, so it's still not decided. Okay, then I choose this I number 2. I choose a causal stroke up here. Then the one junction has found the one and only away from him. The last stroke has to be towards him. The transformer doesn't change anything. And then for this one junction, he's also now found the one stroke away from him. Finally, then I1 gets the differential causality, as it should. Okay, find the equations. Start instantly. Source is known. and we have an x on the other side. I2 is now on the correct form, the effort P2 dot circle on the other side, P2 I2. C, the spring, also integral form. The flow is Q dot circle, effort is Q over C. That's how far you can get sort of instantly. And now we sort of have to look for the continuation here. This one junction, well, I don't know what the flow is here, so I have to start with this one junction here. Who dictates the flow? That's where I'm missing a stroke, so that's P2 over I2 equal Q dot. I found my first equation already. Q dot equals this flow, P2 by I2. Oh yes. And also the flow down here has to be P2 by I2. Then this flow goes through a transformer, sort of the other way. What do we have for a flow on the other side of the transformer? That's 1 over T. So it will be P2 by T, I2. Then I have the common flow on the first one junction, this one. Beautiful. So he goes up here as well. P2 divided by T, I2. Then what do I get on the other side? It's going to be a big expression. I call him A. What is A? A equals, and then we have this differential form for the inertance. That is time derivative of the flow. That read P2 over T I2 multiply with inertance 1. And of course we can do this derivation. It's only P that is a variable here. So I will have P2 dot multiplied with I1 divided by TI2. Then I have my effort here. Now take the summation rule around the first one junction. You have effort in, that's a force, equals what comes out. So what do we have here for effort B? Well, F equals A plus B. Hence, this B must then be F minus A, which I have here. And if this one is called B, what's the effort on the other side of the transformer? Well, that is 1 over T multiplied with B. And then the final equation, the summation rule around the right one junction. So what do we get here? I have the effort, the sum of the efforts must be 0, then the effort P2 dot, he goes out, equals what comes in, that is 1 over T, parameter B, minus what goes out here, minus Q over C, minus Q over C. Now insert B and A, what do we get? 1 over T multiplied with the B, which is force minus A, which we have up here, P2 dot I1 divided by TI2. There, that was 1 over TB minus Q over C. So then we have one equation here and the other equation here. Again, you see you have a P2 dot here, but he appears also on the other side of the equation sign due to the differential causal form. Everybody with me so far? No questions? It's a little algebra here, but shouldn't be too hard. Okay, continuing. I want to check that I get the same answer. Of course, we should get the same answer, but you can't really tell from the equations that we have gotten so far. Hey, now I wiped out that one. What was him? Must be this one. Q dot was P2 by I2, wasn't that correct? Yep, good. Okay, let's rewrite this P2 dot. P2 dot equal, what do we have on the other side? F divided by T. F over T. This term goes on the other side. This we keep. Q over C divided by 1 plus, and then I1 over T square I2. There we have it. Now for the check, we should get the same. Okay. Again, take this one, double derivative, which then equals P2 dot divided by I2. So it's just this one divided by I2. And what will it be? Well, it doesn't look too promising, does it? Should be this one. Let's try. Divide by I2. It will be F over T minus Q over C divided by I2 plus I1 divided by T square. But if you multiply up and down with T square, then you see, yes, indeed, you get the same answer. Of course you get the same answer. But to see it, you actually have to do this double derivative trick. Any questions to that one? Yeah, now the physical interpretation, you mean, of the solution. Yeah, that's a good question. When you do the programming now and you solve it, you simulate this, what do you get? Well, it's a second order system, so here you will get as an answer for the problem or the simulation answer, you will have Q as a function of time, and then depending on did you choose P1 or P2, that's your choice, of course. Say we take the first one, that was P1 as a function of time. So you get these two tables and you can plot them, make some nice curves, and you have no idea what you're looking at, because we use these generic symbols Q and P for any problems, whether it's electric, fluid, rotational, mechanical, whatever. We still use P's and Q's. So in order to translate it back to the physics, then you use table 2.1. Table 2.1 from chapter 2. Very, very important table. Yeah, okay, yeah. Good question. So you have the motion down here, and then you have the spring here. So I called this distance here for x, and this distance for y. So now it's a question, where is Q? Because clearly, from a mechanical point, Q dot, the flow is the velocity, hence Q is position, displacement. But is it x or is it y? But remember where the Q comes from. The Q, he came from the spring. We had the spring on the correct form, so here we had a Q dot. He created the differential equation. When we solve it, we get the displacement. We get the displacement over the spring. Always a delta displacement. So the Q we find here will actually be my y position. The position here over the ground, or just from any zero offset, if you like. Okay. What about the P? P is not pressure. P is not the effort either, is it? A P, that is the time integral of the effort. In mechanical world, what is it? Well, an effort, mechanics, that's a force. According to Newton, that's something to do with mass times acceleration. Okay. Well, and this we then call P dot. What's the time integral? Well, clearly the time integral of P dot, that's just P equals mass times velocity. So it's the momentum. So P1 will be the momentum of mass number 1. So mass times velocity. And there is a lot of mistakes people are doing the first time they play around with the mechanical bond graphs, doing the simulation, and finally just plot these two guys. And then for the P, they plot and get some very strange results, very high numbers, for instance. Well, if you're interested in the velocity, you have to take your P and divide by the mass. So you have to divide by mass to find the velocity. So don't necessarily plot this one directly. You have to divide by mass number 1. Okay? Other questions? In exercise 4, I think there were some examples for this differential causal cases, so you will find something there. The examples here, I believe, is rather boring. They just use some bond graphs that doesn't have any root in a real physical problem. So here's a big example, but I think this one is causal. Okay, we are missing the final outcome, the third outcome. We were left with some bonds without strokes. So we don't have time to do that today. That will be then the topic for next week. And then also, I'll promise you, I will have many, many examples. Any questions? Then we stop here.